Guess it's time to start class. Just a reminder that there's homework due today. Yeah, I think there's homework due today. So I'm going to talk about line integrals today. I guess path integrals. Yeah, let's make that path integrals. So any questions before I get started? All right. So we're moving on to chapter 7. Oh, by the way, there's a great 3 blue, 1 brown video that's related to the last lecture. He's got a video on divergence and curl, which really worth watching, and it's related to vector fields, which was the topic of the last lecture. So anyway, I recommend that everyone watch that 3 blue, 1 brown video on div and curl. So this topic is kind of going to build on that, as you'll see. We're starting in chapter 7 on path and surface integrals. So pretty much we want to be able to integrate over any shape you can imagine, because we started the class talking about integrals over rectangles, and we moved on to integrals over 3D volumes. Now let's start integrating over a path or a curve or a trajectory. So before I introduce the calculus of integrating over a curve, I first want to review curves. So this is a review of material that you can find in section 2.4. It's not calculus yet. This is just actually pre-calculus. You could probably even find it under the topic of parameterized curves in a pre-calculus textbook. So we sometimes use the word path or parameterization or trajectory to mean the following: a continuous map from some interval into Rn. So typically Rn will be R2 or R3. We're looking at curves that are either in space or in the plane in this class. And yeah, so a path is just a continuous map of the interval into space. So they would look, for example, like this. There's a curve. It starts at some point where t is 0, or t is a rather. It ends at some point where t is equal to b, and at each point along the curve, the x and y coordinates are c of the corresponding t value. Sometimes we like to write a little arrow to indicate the direction in which the trajectory is traveled. You will notice that a curve, it's a one-dimensional subset of 2 space or of 3 space. Okay, so we're kind of going down a dimension in a sense in this topic. So here's an example of a path. Let's try the path whose coordinates are given by t and t squared for t in the interval from 0 to 2. And in order to help you graph these, it's sometimes useful to just like plot some points. So I always recommend, if you're not sure what something looks like, well, just try plotting some values of t. So how about I'll figure out what c of t is for a few easy values of t, such as 0, 1, and 2. If t is 0, And plugging in t equals 0 to the equation of the path, I get the point 0, 0, which is at the origin. Plugging in t equals 1, I get the point 1, 1, which is right there. And plugging in t equals 2, I get the point 2, 4, which is right there. So you can extrapolate what the path looks like in between those points. And you see it looks like a parabola, or rather part of a parabola. I'll put a little arrow to indicate the direction that it's going. What about the speed of this trajectory? So the trajectory describes, or you can think of the trajectory as describing motion through time. At each point, you're moving, so you can say what your speed is. Someone tell me, what's the speed along this trajectory? How about at t equals 1? Okay, so in order to find the speed, we first should find the velocity and then take its absolute, or take its norm or magnitude. So the velocity at time t is, well, the derivative of the position, which is 1, 2t. So the velocity at t equals 1, that's c prime of 1, which is 1, 2. If I zoomed into the trajectory and looked at the position corresponding to time 1, apparently we're going, let's see, 1 up 2. This is our velocity, c prime at 1. It's the direction we're pointing in, the tangent to the path or the curve at that time. And its length is our speed. So the speed at that time is taking the magnitude of c prime of 1. That's the square root of 1 squared plus 2 squared. So our speed is root 5 right at that time. Okay, any questions? Here's another example. How about the path whose components are t comma t, with t between 0 and 1, and t comma 2 minus t, and t is between 1 and 2. So in order to figure out what this path looks like, again, I'm just going to plot a few points for t, and then I'll see what c of t is. How about 0, 1/2, 1, 1.5, and 2. So I'm plugging in those values of t to this equation. I get, let's see, 0, 0. 1/2, 1/2, 1, 1. Let's see, if I plug in 1.5, then I better use the second equation. Right, so this is an example of a piecewise defined function. And since t equals 1.5 is in this range, this is the equation I use to determine the coordinates. And I get, let's see, that's t is 1.5, 2 minus t is 0.5. And at t equals 2, I get 2, 0. Connecting the points, we can extrapolate that the path looks like that. We would call this a piecewise C1 curve. Because it's made of two pieces, this piece and this piece. Each piece is C1. It's not C1 where they intersect, where they meet. So right at this point here, the curve is not differentiable, right? Like which way would the velocity be pointing? Would it be pointing that way or would it be pointing that way? The derivative would not be defined right at that point. But on the first piece and on the second piece, respectively, it is C1. So for that reason, we would say that this is a piecewise C1 curve. And okay, any questions on this one? Here's a useful fact that will help give you an idea of what a curve looks like. If you write the curve where the first coordinate is just t, and the second coordinate is some function of t, well, that curve is going to lie on the graph of that function. Just like in the first example, the curve was on the graph of x squared. It didn't take up the whole graph, but it was on the graph. It was a certain portion of the graph. Here's a challenge question for you. Find a parameterization of the curve connecting, let's say, the point AB to the point CD in a straight line segment. Okay, so I'll let you try that. There's many possible answers, by the way. That's why I say find a parameterization. And let me ask the class a yes or no question. Yes or no? A circle is the image of a curve. Yes or no, folks? Is a circle a curve? Okay. Yes. Yes, it is. It's a particularly important and useful parameterization. So I'm going to show it to you now. So here's how here's one way we can parameterize a circle. Cos t sine t is one of the many ways that you can parameterize a circle. where t ranges, say, from 0 to 2 pi. So when t is 0, we're at the point 0, 1. When t is pi over 2, that's when we hit the y-axis. And as t moves through 0 to 2 pi, we travel once around the circle and end up back where we started. We would describe this motion as counterclockwise. Anyway, I would challenge you that to try to come up with, say, a clockwise parametrization of the circle, or how about one that starts at some other point? Sorry, 1 second. Anyway, related to the parametrization of the unit circle would, for example, be a parametrization of an ellipse. So one of your homework problems asks you to come up with a parametrization of an ellipse. So it's kind of similar to this parametrization. And you'll see that when you do 7.1 number 4. Okay, so that's all the review. Now it's time to get down to calculus. So moving on to 7.1 path integrals, and we're going to assume that all our paths are continuously differentiable, and we're going to confine ourselves to the plane or to space. Here's the definition of a path integral. In other words, the integral of some function over some path. Let's let C be a path. This is in R. I'll do the definition in R3, although the R2 definition is similar. So C is a path with components x, y, and z, each being some function of t, and t will be in the interval a to b. And our integrand, f, will be some continuous real valued function. Then the path integral of f over the path c, or along c, is as follows. We'll notate it with a single integral sign with a subscript over the curve that we're integrating over. Our integrand is, well, the function that we want to integrate. This book's notation is usually to use ds. I don't know why they chose s, but they chose s to mean like your little path length element. So that's the notation for the path integral of f along c. On the right side of this equation is how to actually compute it. So you might wonder where the heck this formula comes from, and I'll get to that later. For now, let me just tell you what it is. So you're going to integrate from t equals a up to t equals b of the function f evaluated at points on the curve times this factor, which is the speed of the curve, the speed of the trajectory, and all integrated dt. A couple other ways of notating this might be where instead of f, we explicitly mention that it's f of x, y, and z. Or here's another nice way. You could say f of the curve of t times the length of the curve. So all those different ways are ways of notating this. And this is the definition if the curve is C1 and if the function f itself is also continuous. But if the integrand here is not continuous, but can, or sorry, yes, if this integrand here is not continuous, but can be broken up into pieces that are, then in that case, you can still integrate the function over the curve by just writing it as a sum over the different pieces. Okay, so you break up the integral into the pieces where the integrand is continuous and sum the integral over those. Okay, so that was a lot of talking about the definition. Let's just see an example, and it'll probably make a bit more sense. How about the curve given by C of t equals cos t sine t t, and f is the function f of x, y, z equals z. So let's integrate this function over this curve. First, how about I try and visualize what the curve looks like? So if I plot some specific values of t, let's see. Say this is pi and 2 pi. So this is going to go through the point 1, 0, 0. C of 0 is 1, 0, 0. C of pi over 2 is 0, 1, pi over 2. C of pi is -1, 0, pi, and C of 3 pi over 2 is 0, -1, 3 pi over 2, and C of 2 pi is 1, 0, 2 pi. So connecting these points, let's see. Okay, so we would call that a helix, right? It's kind of like a single strand of DNA wraps around the z-axis. Now let's start computing the integral of f over that helix. So let's see. Oh, I guess I'll need the speed. So take the derivative of the position. That's going to be negative sine t cos t 1. So that's the velocity. So the speed is going to be sine squared t plus cos squared t plus 1, which is just root 2. So that's nice. The speed is constant throughout. According to the new path integral formula, the integral of f ds over this curve will be the integral from, let's see, t starts at 0 and ends at 2 pi. F of c is z, which is t. So I have a t right there. So there's my path. Any questions of that? Questions on that? Oh, and there's an image of a double-stranded helix, which is the form of DNA. DNA is made up of a double helix. So you can actually do the computation here. It'll be root 2 times 1/2 t squared from t equals 0 to 2 pi. So that's root 2 times 1/2 times 4 pi squared, which is 2 root 2 pi squared. Keel asked what f is supposed to be. F is given to be z in this question. So in general, it's whatever the function that you want to integrate over the path is. In this case, it was just z. Now, let me explain a bit about where the heck the path integral formula came from. So I'm going to give like a light explanation. It's not going to be super rigorous, but I'm also trying to not just like give you formulas and not give you any idea of where they're from. So I'm going to do another example now. And in so doing, I'm going to try to motivate or at least give some explanation of where the path integral formula came from. So I will do that in the context of the following example. Example 4. How about now, let's let C be this path here. The coordinates being cos cubed t and sine cubed t. And let's let f be the function 1 minus x. So this is now a two-dimensional problem. Although, if you tried to graph a function of 2 variables, the graph lives in 3 dimensions. So just note, in the last example, we couldn't even visualize what the graph of the function looked like because we would have needed like a 4th dimension. In this example, we actually can visualize what it is that the function looks like and what the integral looks like. So first, how about I'll plot the curve C, and I'll just tell you what it ends up being. It starts at 1, 0. That's where t is 0. And it ends at 0, 1. That's where t is equal to pi over 2. And it does so in like a curve like that. Okay, so there's the path C. What about the function? So I'm going to try to draw the function as living on top of that path or that curve. The function was 1 minus x. So for example, at the point 1, 0, f is also 0. At the point 0, 1, f is 1 minus 0, which is 1. And in between them, it smoothly goes up like that. So this ridge right here represents the value of the function at over each point in the curve. And the integral, check this out, the integral that we're trying to calculate, it's like the area of this fence. If you want to imagine that this is like a fence, it's a curvy fence. The height of the fence is increasing. Let's find the area of that fence. Okay, so that's what we're computing here. There's a solid physical interpretation of what a path integral equals. So let's find the area of this fence right here. And in order to do so, or in order to explain where the formula comes from, let's chop the time interval into sub-intervals. And so let's say that t equals 0 is like t0. And let's say that pi over 2, that's like t sub n. And in between, we'll have a whole bunch of other ones. So say this point would be where t is t1. And let's say that this is where t is ti, and this is where t is t sub I plus 1. And in fact, I could also write that as ti plus, let's just say delta t. So we're increasing t by an amount delta t. So the trajectory position has a certain increase as well. Let's say in going from this point to this point, the trajectory changed by an amount, I'll just call it delta c sub I. Now, if the change in time is very small, then we can approximate the change in position on the trajectory by just imagining that the motion was in a straight line at constant speed. And I'll do that in a second, but let me also draw the portion of the fence that we want to approximate. So that would be this part right here. Let's call this delta A. How about? So we're chopping the fence into a bunch of fence boards, if you will, and we're going to add up their areas. Okay, so that's the setup in this picture. This is the area of the fence, and it will be the sum of each of the delta A's. Now, if the change in time is small, then the delta A's will approximately be rectangles. This argument that I'm about to make, by the way, it's probably going to be a bit confusing, and I'm deliberately not going into full detail, but if you have questions or want to know more, I'd be happy to explain it after class. So here's the idea. Delta is approximately a rectangle with height. Let's see, what's the height? That would be this length right there, which is f of c of ti. And the base is given by the length of delta ci. But if Ti is very small, then we can approximate this by C prime of Ti delta T. Okay, so that's another place where we're making an approximation. So let's add up all the fence boards. As I said, each of them are approximately rectangles, where this is their height and this is their width approximately. So with those approximations, the area of each fence board is approximately F of C of Ti times the width of the base, the length of the base. Now, does that expression look familiar? I don't know, maybe, depends how comfortable you are with Riemann sums, but as you let the number of subintervals go to infinity, this approaches the integral from a to b. Well, in this case, from say 0 to pi over 2 of f of c of t times c prime of t delta t. So that's the proof of where the heck the path integral formula came from. And I brushed over this inequality or approximation pretty quickly. So like I said, that probably is a bit confusing to some of you. Some of you may be wondering why that's true. And I can show it more rigorously in office hours if anyone wants to see why that's the case. For now, I'll just leave it at that. So finishing off this question, let's do the actual computation. In our case, we will have then that this is the integral from 0 to pi over 2 of, let's see, f was, oh, I need to compute the speed, sorry. So let me do that first. C prime is, since c is cos cubed, c prime will be 3 cos squared t times sine t. Sorry, negative sine t. 3 sine squared t times cos t. You can check that the speed in this problem ends up being 3 sine t cos t. So doing that calculation is a good exercise. Again, I can show in office hours if anyone wants to see how or why. So the integral of f over this path will be the integral from 0 to pi over 2 of f is 1 minus x, so it's 1 minus cos cubed t. The speed is 3 sine t cos t. And if you work this out, you find that this is equal to 9 over 10. Again, if anyone wants to see how or why, I can show you in office hours. I'll just leave it at that for now. Any questions on this problem? This was a combination of example and proof. Cool, okay. Well, then I guess we finished that one. Yeah, 9/10 is the area of the fence. If you use the path integral formula and you just let your integrand f, the function, be 1, that's kind of like finding the area of a fence with height 1. Right? I imagine we have, I don't know, some path in the xy plane, and then we have a fence above it, but the fence is of height 1. Well, in that case, the area of the fence will be the same as the length of the curve. And in fact, in theory, you're supposed to have already learned or seen this formula, the arc length formula. So that's what you get if you let f be 1 in the path integral formula. You recover the arc length formula. And this is in section 4.2 in the textbook. Let's see, let me ask you a question. How about if C of t is cos t sine t with t from 0 to 2 pi, then L of C is what? Someone tell me this. It's a big test on all the new notation. Ooh. 2 pi. Yes, it is 2 pi. Because as we saw earlier today, this is a parametrization of the unit circle. So the length of one trip around the unit circle is 2 pi. That's the length of that path. Now that we've defined arc length, or now that we have a formula for arc length, we can do my favorite kind of problem, which is averages. Yeah, so you've probably figured out by now, especially after taking that midterm, that I love asking averages problems. Oh, hey, so what did y'all think about the pecans and raisins problem? It's pretty cool, right? It's a good physical explanation of the tasty, right? Yeah, it was a tasty problem too. Hard, yeah. It was meant to be the hardest for sure. And if you look at the solution, it's not that hard. Actually, the second part of the problem doesn't even use much computation, actually. But yeah, I thought it was good for providing a physical intuition for the difference between a average over a surface versus the average over a volume. It's the pecans versus the raisins. Anyway, I can talk more about that later. Let me give you the average formula for the context of paths. So the average of a function over a path will be the integral over the path divided by the length of the path. Let's try applying this formula to the last example. So in example 4, remember we were asking for the integral, that which is to say the area of this fence. This was the graph of f. Let's find the average of f over this curve. Before we do, I want to make a Zoom poll and guess it. So I'm going to give you 4 choices. So let's find the average of f over c. And before we do, I want us to guess whether it's more or less than a half. So let's say A is that f average is less than a half. B would be that f average equals a half. C would be that f average is greater than a half. And D will be no idea, and I refuse to guess. So we'll find it exactly. For now, just take a guess. Give it your best guess. And you can use the picture. So it's kind of like, on average, where does f spend most its time? It's definitely between 0 and 1. At this point, f is 1. At this point, f is 0. So it's somewhere between 0 and 1. Does it spend more time closer to 1 or more time closer to 0? Okay, about 10% said less, 33 said equal, 7 said more. Okay, so let's actually do it now. Here, I'll do it right here. So the length of the path C will be the integral from, let's see, it was 0 to pi over 2 of the speed. This is the integral from 0 to pi over 2. The speed, I already mentioned, actually, what was it? It was 3 sine cosine. Yeah, right there. So let me just plug that in. The integral of 3 times sine times cosine. It's 3 times 1/2 sine squared t 0 to pi over 2, which is 3 over 2. So the average value of f will be 1 over 3 over 2 times 9 over 10. We get 3 over 5.6. So it looks like most of you that said greater than 1/2 were correct. Now you can see why it's greater than 1/2, because if you look at the curve, it spends more time closer to the y-axis, which is where f is closer to 1. Okay, let's see, was that Let me check something. Is that the end of the lecture? Oh yeah, good. Wow, I finished right on time. Perfect. Okay. That is it, folks. Thanks for watching. See you all Friday. Hang out for questions.
Thank you.
Yeah, you're welcome. You're welcome, folks.
I have a question.
Mhm.
So can we see this this kind of curved rectangular shape is like rectangular when you when you straighten it up? Is it? I mean, in this case, it shouldn't, right? Because if this was if it is not a curve, we can just take it off the coordinate system and just kind of straighten it up to be a rectangular, and then the average height in this case it should be half.
You're asking if the curve is straight?
Yeah.
So yeah, the curve is like that. So it's
Right.
not straight. And if it was straight, then you would be right. The average would be a half.
Yeah, because what I was thinking is, let's say if it is not a rectangle, let's say it's just like instead of fx equals to 1 minus x, let's just say fx equals to a constant equals to 1, and then the area of the fence of the surface would just be the length of the curve and times the height, right?
Yeah.
And if it were 1 minus x, I was assuming it would be exactly perpendicular point to point below the curve. So I was thinking maybe it is a rectangular when you.
Wait, what's a rectangle?
I mean, it would be a triangle after let's say you took the curve and then you kind of just put in a straight line.
Okay. Yeah, good point. So could we sort of flatten it out and straighten it
Right.
out? Because so these are the set of points cos cubed t sine cubed t. That's the curve. And f is
1 minus
1
x.
minus x. So f on the curve is well, 1 minus cos cubed, although what if, let's reparameterize this curve. So that's C of t. A reparameterization, I haven't worked this out beforehand, so I don't know how this is going to come out, but a reparameterization of C, how about if I just made one of the coordinates equal to t? Might be, let's see, what's a name for it? How about d of t equals t comma what? This is kind of tricky. So it's like, how about set this equal to s? How about, maybe I should let's use the letter s. So if I set cos cubed equal to s, then what is sine cubed in terms of s? So if s is cos cubed t, then
That would be just 1 minus 1 minus the cos cube s to the 2/3 and parentheses the whole thing to the cube.
Okay, yeah, sine
That's what I thought.
Sine of cos inverse of the cube root of t, all of that cubed. So let's see, sine of cos inverse is square root of 1 minus you say t to the 2/3, and then all of this cubed. Is that what you said?
Okay, let me see. T, that's T. Yeah, that's T. So if we, what I was saying, if we set up the cosine to the third t to be x, so that would be just the one that you selected, but if instead of the outside of the parentheses, instead of the 3/2, it would be to the power of 3.
If you said if x is cos cubed t.
Yes.
I think
But I feel that in this case, it's more like a change of a coordinate system. It's more like a notation. It's like mapping from one surface to the other surface.
well, I did it by letting s equal cos cubed of t, and in that case, the other coordinate has this equation. Or maybe sorry, I need it. This is a s. So another parameterization would be d of s equals s.
Oh yes, you're right. You're right.
1 minus s
Yeah,
to
let's
the
just go.
3 halves, or 2/3, all to the 3 halves.
Yes, you're right. And after doing the integral of the equation that you just came up with, and we should get the arc length, because this is but instead of to the respect of t, this would be to the respect of s, and s just goes from 0 to 1.
So if you read, let's see, so f on d is 1, well, it's 1 minus s. So if we wanted to express it as like let's see, how should I say this? have to do a transformation. Let's see. The path length.
This is the part I couldn't figure out because like you said, I have to do a transformation from one coordinate system to kind of mapping onto a different set of coordinate system to be a straight line.
So there's a couple ways that I'm thinking of that might work. So you could define like a transformation, which takes, let's say, I don't know which segment you want to take it to, like this one or anyone. How about let's just do this one, which, but you could have, let's say, t of x xy. Let's see. Okay, well, you can decide where you want these points to go. So if t of s1 minus s2 s to the 3 halves is equal to, I don't know, how about s1 minus s or s0. Let's say, how about just s comma 0, then right now, let's do it. If you can measure the arc length distance function from this point as a, say, a function of t or s up to this point, that would be, let's say, L of S. So the integral, let's see, from 0 to, let's just say, S v sine t cos t dt is 3 over 2 times 1/2 sine squared S. This goes from 0 to pi over 2. So as a function of cos cubed cos cubed of S as a function of S. It's the cube of square root of 1 minus 2L over 3. Okay. Yeah, I think that that should be it. So if you plot something like 1 minus let's say 2x over 3 cubed, I think, let's see, if I did this right, when x is 3 over 2, it's 0. And when x is 0, it's 1. I think that should look something like that. So let's see, what's 1 minus all right, yeah. Okay, so there would be your straightened out fence. The portion from 0 to root 3 over 2.
Okay.
And you can see that the average,
That
let's
is
see,
more curved to
if, let's see, maybe this is a check. If I integrate this from 0 to 3 over 2,
Okay.
Um, yeah,
This is pretty cool. I don't know OneNote can do this.
sorry.
I said this is pretty cool. I didn't know OneNote can do this.
Yeah, yeah. Neat.
Okay. Well, thank you. Because I was thinking about the fence not being a incline or upcline line, not like f equals to 1 minus x. I was thinking the example that you said about like a curved line, and then with just like the fence, like straight up the fence, and I was thinking, oh, if you straighten it out, it's just like rectangular. And maybe you straighten it out in this case, it's just maybe like a triangular. And guess not.
Yeah, I mean, you could stretch it. You could apply another transformation that well, let's see, would that make it a yeah, forget what I was about to say. Yeah.
Well, thank you.
Yeah, thank you. Yeah, cool question.
Okay. Oh, and also